here we're going to explore actually 3 different types of joins, actually 4 different types of joins that you can do in pandas. We're going to populate our database with a couple more tables than we have seen earlier. In this, we'll have actually 7 different tables, but we'll only be working on a couple at a time to keep things nice and organized. So, in our first example here, I'm curious, nan filling or null filling in SQL. In pandas, we have very flexible null filling. We can fill an entire table where nulls exist with some sentinel value. We can fill specific columns, right, with specific values. And this might be the trickier one. We can fill one column with values from another column, right? So we can fill in the nans in values 1 with the data from values 2 if it's not nan or null itself. So James, how do you go about filling null value in SQL?
Remember, the core mechanic of SQL is operating on individual tuples and operating on sets of those tuples and transforming sets of those tuples. Anything that you can do looking at just one tuple at a time is as easy as it would be in pandas. And so here, the filling of nans here, let's quickly take a look at what we have in our data set. And we've got a couple of nans there. They print out really nicely on our screen. We want the nans for values 1 to just take the thing from values 2. And so here, we could do a coalesce. And we could say coalesce values 1, values 2 for each ID as our value. And the one tricky thing is the tuples that you get from SQL are strongly typed. And so here in pandas, you could always have that object D type. Here, this might kind of, fall apart on you. So you can think, in this use case, it might not be that it might not be that relevant, but you could do something like this. Or you can always use a case statement in SQL. You can always do something like case when, or case values 1 when, I don't know if when null. We'll do it this way. Case when values 1 is null, then whatever, 0 else values 1. And as long as you're largely staying within the type system, SQL will be fine with this.
Perfect. And I actually want to stay on that. Since you brought up the idea of working within these tuples is very easy. And I promise you I can do this in pandas. You're just going to have to trust me on it. But pandas allows us to very easily forward fill our nan values column-wise and or backward fill it. Right? So if we have a nan in row 4, we can fill it with the last seen value, say in row 2 or row 3. As long as there wasn't a nan there, we can forward fill that column down. Is that hard to do in SQL?
I could do it, but we can see where the mental model breaks down.
Yeah.
Pandas, in-memory data with an implicit ordering, and you can easily access the data before or the data after. That's pretty trivial. In SQL, you're operating on the individual tuples. So there's no implicit ordering for this. There's the ordering that you perform as an operation in an order by. There's the display ordering or the computational ordering, the projection that you produce. But there's not really an implicit ordering. There's on-disk ordering, but remember, these are asynchronous systems, so the on-disk location of the data, who knows what that really represents, right? So the only ordering that you can bring into SQL is the ordering that you bring in terms of column values. And how those are actually represented on disk in a multi-tenant asynchronous system, who knows? In your case, you want to forward or backfill. And to make that meaningful, what we'll assume is that there is a natural ordering from the data. So there's that ID column, and it makes sense to forward or backfill. With the coalesce or the case or the simple select, you cannot look at more than one tuple at a time. You can look within that tuple easily, but you can't look at the tuples before or the tuples after. Here, what I would suspect you would do is you would have I think we can do a coalesce over a window. So that might be the closest that we can get. And so here you're going to do, let's see, we'll try coalescing this thing over a partition by ID. Yeah, we'll do it like this. Partition by, no, we don't want a partition. We'll do over order by ID. And No, I guess you can't coalesce over. So here, we have to go back to our list of window functions. We'll have to see what window functions we have. That's kind of tricky.
Fair enough, yeah.
So.
I think it's safe to say that this might be a trickier operation, right? Whenever you're looking outside of those tuples, outside of the rows, you really have to push that mental model that you have into something and make SQL do something that it's not too keen on.
I know how we do this. We do this with a join. We join the table with itself, and then for each row, we'd see all the rows that are before it. That would give us a group by, and then we'd, within that group by, order those, and then from that ordering, we could figure out what the last non-null value is.
Fantastic.
Because we could filter out the nulls and then find the, one value ordered.
Yeah, that sounds like it would work to me, but we have plenty of more questions that I want to get to, so we'll move on to those. In this one, maybe a little less interesting, so you can give us the very quick response. We have 3 tables. One is our kind of base table, and it has a one-to-one relationship to the one table, and the base table also has a one-to-many relationship to the many table. Pandas offers a ton of different operations in order to perform these joins. We can merge on specific columns. We can perform a left join, right join, outer join, inner join, a cross join, which is actually fairly new in Pandas. And I want to show you something about the cross join that upsets me. When you output it, the index is not the Cartesian product of the 2 columns that you joined on. Ridiculous. But I know you can do a Cartesian product join on 2 tables. What I'm interested in here is actually this. In other languages, this is called an anti-join. Pandas does not have an immediate function available from it, so what you have to do is perform an outer join and then drop the rows where that index was shared, or that column that you're merging on was shared, so that you end up with a table who only has unique keys from the left and right. So your resultant table only has the unique left values and the unique right values and no shared values.
Here's the thing. Unions, differences, except, things like that are not hard to do in SQL. Joins are natural in SQL. In fact, I would argue that this is one place where SQL is better than Pandas. Because yes, you can do a join or a merge in SQL, and you can do it on the index or on a specific column, but can you do it on an arbitrary computation that includes external data, or can you do it in an arbitrary computation of the column without forcing that to be a synthetic column? You cannot. Whereas in SQL, because you get that clause, inner join on, you can put anything in that clause that looks at one row of one of the tables and one row of the other table. And if you want to use some synthetic data, you do an inner join there. Or if you wanted to use something that was external from that, like a random number or whatnot, you could just put any arbitrary expression. So basically, any expression that you can compute on the combined tuples of 2 tables, you can do a join on without having to create a synthetic column. In SQL, you can see I can do joins where I say give me all the previous values, join one table against all the previous values. It's not expressible in Pandas. And things like the anti-join might not have a nice syntax. You can't just say inner join, anti-join on or whatnot. But in general, what you can think is any combination of tables, unions, except, differences, those kind of things, are doable in SQL. And they're relatively easy to do, and then in some cases may be much more flexible and much more powerful than what you have in Pandas.
Fantastic. Yeah, and as I said earlier, Pandas, the joins on these data frames are all based on SQL. So it makes sense. As a relational database tool, the joins should be extremely powerful and extremely flexible. Moving on. Pandas has some actually flexible joins in itself, and I'm very, very curious about this one. It can perform what's called a nearest match join. This is very useful when you're working with things like dates, or like you want to join on continuous data columns. And essentially what will happen here is you compare all the values in your left table to your right table. Essentially you get the Cartesian product of these, You find the differences, and you find the rows where that difference is minimized. And so you end up with actually a very interesting join. I'm going to show you what happens when I print these tables and try to perform a standard merge on them. You can see I get nothing in the output because my start date and my end dates, they're not, uniform timestamps. They are just kind of sampled at different rates, and so we can't really join on them since they don't align. But what the merge as of function allows us to do is to take each timestamp in our left column, compare it to each timestamp in our right table, and find where that difference between them is minimized, and we can even do it, we're doing it backwards in this case, so we're only searching in one direction. And this is telling me that at my start date of 2020, January 2nd, there was no date in my right-hand table that happened before that. Now my next row in my start date of January 4th, there happened to be one date in my right-hand table that was just before that, and so that's what we merge on, and so on and so forth for our last column. Can you perform this type of join with SQL?
Absolutely. And this is one where you're going to have to find some contortions because there's one or two important qualifications on how this works in SQL. But I'll show you what I would do. First, what we know is we want one row per each input row that you have. And we just want to have whatever input row matched like the previous one based on some criteria. So what we'll do is we'll select star from our data. We'll inner join this, or we'll do a Cartesian product here. So we'll do this against data as D1. We'll take a look at what this gives us, and let's do a limit here, otherwise it's going to spam our screen. D0.star and D1.star. You want from this to then filter this down to all the rows for D1 and D0, all the rows that came before. And it's not too dissimilar from what we did before, so we'll switch this over to be an inner join. Inner join data as D1 on this. We'll get D1, and we'll have this date be greater than or equal to D0. Actually, we'll make this like this, and we won't join a row against itself. So we'll say the unique identifier is not the unique identifier here. So here we go. Now we have the Cartesian product of every row, and this would be ID here. There we go. And so now we have the Cartesian product of every row and every row which came before it. You just want the earliest row that came before it. You just want this row and the one that's immediately preceding it. And this is where it gets a little tricky. What we would need to do in order to subset this is either filter it or group it. Can we filter? Remember, filters only look at one tuple at a time. From one tuple, we cannot tell if you're the nearest match or the furthest match because that requires looking at multiple tuples at a time. So necessarily, we're going to have to do some sort of grouping. And if you think about it, our target is the D1. That's what we're trying to find everything that was before. So we'll probably group by D1.id. And when we group by D1.id, we can see each row that we got. Now, when we do this, we can do a quick array ag, and we can see which D0 ID rows we have. And you can see how, we get this information. And I wish we had, So let's do a couple more rows just so you can see. And you can see here this matched, the data was sorted in some fashion, so you can see it's just kind of pulling everything here. And I think if we keep expanding this, we'll eventually see this thing reset, unless there's a lot of rows before. Do we want to do this with a categorization as well? Or we wanted to match everything within a category, or just everything before every row? No, you just want everything that was immediately before this row. So this is just going to grow
Yes,
forever.
I want the closest thing before, yeah.
Yeah. It turns out that here, what we'd have to do is we'd have to kind of subset this. But this actually already exists in the window function very, very delicately, I should say. We can try to put this together. What we can do is we can select everything from the data set, and we can actually lead and lag in the window function. So I think what you might actually want here is something like this. But you want the, we'll order and do a lead a lag. We can do this with the window function. And then I'll show you how to do it with the group by in just a moment, but we'll do this. Here we get the ID. we get the lead 1 dot value 1 from over partition or over order by ID, like this. And I have to remember how that looks. This is, oh no, this is comma and then the element name, I believe. Okay, what are the names of our columns here? Let's find out. Yep, value 1. So then we order this, and this is the, I think it's the other way around. I think it's the column that we want, and then yeah, there we go. So that's the immediately preceding value, or the lag. You know, it's kind of like the shift. I can remember which direction that goes in pandas. And then that would give us that value, and then we can compare that against something else. And so that might be one way we do this, but here we can't say the previous value that was non-null, because we can't look at that value. We can just say the immediate previous value according to some ordering. Here, we could actually do things like say the previous value that was non-null, because we could add an arbitrary condition to the joining to extract those. And here you can see we have every row and the immediate preceding rows. Well, the trick that we might do here is we might identify we might group by the ID and then identify what the maximum D0 ID was for each one of these groups. So now we know each row and the previous row, and this gives us something that we can join against. We could do this in a CTE. These are our matches. And then we could do something like this. Select star from data as D0, and we can interjoin on, actually we can just do this as a simple from clause, data as D1, and we could say where D0.ID equals, and we'd have to join this, interjoin on matches, or interjoin matches on, M dot, the left-hand side equals D0.ID, and M dot the right-hand side equals D1.ID. So we can do this here. And so most of this is a little bit more contorted than we might like, but for the most part, I think this should work. I think the one thing, D0 here, we got both of those, D0.ID. We do have an ID column on these. That should be good. And here we can just do another inner join here. On m.right equals d1.id, and then we just do a filter here. No, we still have to do an inner join, but we can kind of coerce the join a little bit just to get this working until we have exactly what we want. But fundamentally, we have to first pre-compute that and then go there.
Yeah.
But we can have arbitrary complexity in how we do that joining. So we could find the first preceding value that satisfied an arbitrary preceding predicate.